Good day to Doctor. Today we are going to be presenting our discussion for a group project which is titled The Techniques of Differentiation. This is for our assignment 2 and will be presented in stages by myself, Alfred, Nur-Ain as well as Daniel. So basically these are our team members. At the top left you have Ain, on the right Alfred, bottom left is myself, Arina Malaysian referee, and lastly we have Daniel Hakim on the bottom right. So now I will begin by explaining the meaning of differentiation and the techniques of differentiation. So in calculus, differentiation is one of the two important concepts apart from integration. The process of determining a function derivative is called differentiation. Finding the instantaneous rate of change in a function depending on one of its variables is known as differentiation in mathematics. The most common example is velocity, which is the rate at which displacement changes in relation to time. Also, anti-differentiation is the opposite of differentiation. So next, we are going to be discussing the applications of differentiation. So usually we use differentiation to first find the slope, second to determine whether intervals of a function increases or decreases, and third, finding or calculating the velocity as well as its acceleration. So now we are going to proceed to the techniques of differentiation. Firstly, we have product rule. We use it to differentiate a product of two functions. So the formula is d over dx fx equals to uv prime plus vu prime. Then we have power rule. Usually we use it to differentiate polynomial terms. So the formula is d over dx xn equals to nx n minus 1. Then we have the quotient rule, which is used for functions written as one function that are divided by another. So the formula is d over dx fx equals to vu prime minus uv prime over v squared. And then we have chain rule, when one function is inside another function. So the formula is dy over dx equals to dy over dux times du over dx. So next we have the constant rule, where any constant value does not change. So the derivative is 0. So the formula is d over dx c equals to 0. And next we have the sum and differences rule, which is used to differentiate multiple terms which are added or subtracted in a function. So the formula is d over dx fx positive negative gx is equals to f prime x positive negative g prime x. So that's it for the techniques of differentiation. Now let's see for the questions. So basically we are asked to find the derivative dy over dx for the following functions. For part A, this question looks like a product of a polynomial and a trigonometric function. For part B, this one is a rational function involving a sine function inside the denominator. These two are perfect examples of functions that require the product rule, quotient rule, and some chain rule action to differentiate correctly. In the next slide, Alfred is going to take you through each one step by step and show you on how to solve each question.
Alright, thank you Adina. My name is Alfred and I will be explaining on how to solve this question. So you might be wondering what kind of rule we can use for this type of question. The most suitable rule to be used is product rule, and here is the formula. As you can see, for x squared is our u. We then differentiate it, it becomes fx, and that is our u prime. Then cos bracket 5x minus 2 is our v. We then differentiate it to get negative 5 sine bracket 5x minus 2, and that is our v prime. The next step is place each term accordingly by using the product rule formula. Next, simplify that, and that is our final answer for this question. For the next question on how to find the dy over dx for y equals 3x plus 1 over sine bracket 2x is, firstly, when we see a quotient in the question, we can use quotient rule for the first step to solve this question. Here is the formula for quotient rule. We then take 3x plus 1 as our u. Differentiate it, then we get 3 for our u prime. Next, we can take sine bracket 2x as our v. Differentiate it, then we get 2 cos bracket 2x for our v prime. We then place each term according to the quotient rule. Simplify the equation, and our final answer is dy over dx equals 3 sine bracket 2x minus 2 bracket 3x plus 1 cos bracket 2x over sine square bracket 2x. This is all the steps to solve these two questions. I will end my presentation here. Thank you.
Hi, my name is Nur-Ain Abdullah. My student ID is 2023160003. To solve this question, we are asked to find dy dx using implicit differentiations. So we start by differentiate both sides of the equation with respect to x. Since we have y terms, we will apply implicit differentiation, treating as y as a function of x. So let's begin with the left hand side. So the first term is y ln to x. This is a product of two functions, so we apply the product rule. So we will differentiate the first term, which is d over dx y ln to x. So the answer is y times 1 over x plus ln to x dy dx. So how we differentiate this term? We will using uv prime plus vu primes. So u equal to y, v equal to ln to x, u prime equal to dy dx, v prime equal to d over dx ln to x. Then we will simplify it, 1 over 2x times 2, and then the answer is 1 over x. So the second term is d over dx, exponent 5x plus 3. The answer is exponent 5x plus 3 times d over dx, 5x plus 3, and then it simplify it again, e exponent 5x plus 3 times 5, and then final answer is 5e, 5x plus 3. Okay, now for the right hand side, we use chain rule, which is d over dx 10 6y equal to secant square 6y times d over dx 6y, and then secant square 6y times 6 dy dx, and the final answer is 6 secant square 6y dy over dx. Okay, now we combine all the parts, which is y times 1 over x plus ln 2x dy over dx minus 5 exponent 5x plus 3 equal to 6 secant square 6y dy dx, and then we factor out dy dx, we become y times 1 over x plus 1 to x minus 6 secant square 6y equal to negative y over x plus 5 exponent 5x plus 3. To get dy over dx by itself, I divide both sides. Here is an easy way to remember it. The top part of the fraction, numerator, is the side without dy over dx, which is negative y over x, 5 exponent 5x plus 3. The bottom part, denominator, is the expression that was multiplied with dy over dx, which is ln 2x minus 6 secant square 6y. So finally, we get negative y over x plus 5e exponent 5x plus 3 over ln 2x minus 6 secant square 6y.
Hi, my name is Daniel Hakim, and I'm going to answer the last question, which is question number 4. So the question is, use linear approximation to estimate the value of cube root 63.98 minus 2 over square root 63.98, correct to 3 decimal places. So first, let's define the function so we can apply linear approximation. So we have fx equal to cube root x minus 2 over square root x. Next, we're going to rewrite it using exponent. Why? Because this makes it easier for us to apply differentiation like rules, power rule. Next step is to find a number that is close to 63.98, which is 64. Why 64? Because it is the closest one, and we need to plus minus 0.02 to make it 63.98. After that, we're gonna derive the fx, and we will get the derivative of f prime x equal to 1 over 3x power negative 2 over 3 plus x power negative 3 over 2. And then the following step is to plug the 64 for both fx and f prime fx. So as you can see, for the fx, we plug in the 64, it will be equal to 15 over 4. And for the prime fx, it will be equal to 35 over 1536. Then we need to use the linear approximation formula, which is, as you can see, the formula is there, and then I'm gonna use the f64 plus f prime 64 multiplied with negative 0.02, and as you can see, it's 15 over 4 plus 35 over 1536 multiplied with negative 0.02, and then we will get the answer, which is this 37495, and then yeah, that's the answer. And lastly, we will round the final answer to 3 decimal places like the question wanted. And yeah, that's all from me. The final answer will be 3.750, 3 decimal places. Thank you.
So I'm sure that everyone wonders the same thing. How do I master differentiation? It is actually quite easy. Firstly, we can memorize and practice the rules. We have to know the rules like the back of our hand, as these rules form the backbone of most differentiation problems. Secondly, we have to be able to recognize patterns very quickly. We have to be on the lookout for function structures. And third, we have to check and simplify our work. We should always go back and see if our solutions can be simplified, as clean math is easier to understand and it is less prone to errors. And lastly, we have to stay curious and keep on practicing. The more we explore these techniques and rules, the more confident and flexible we become in tackling calculus challenges.
To sum up everything we have done, this task really deepened our understanding of differentiation. We explore its basic concept, apply various rules, and work through more complex ideas like implicit differentiations. Using linear approximation also showed us how calculus can be applied in real-life situations. Overall, it strengthened our skill and highlighted how practical and useful differentiation is.